This is geotrig. This is lesson 12. Actually, this is the last part of lesson 11 because we did not officially do an example of the quadratic formula. What I want to do today is finish up lesson 11, then go into 12a, and then we're done with 12. I'm going to leave the proofs to you guys to look at. They're pretty interesting. They're fairly easy to follow, but to save a little bit of time for us, we're going to skip those. So we're going to do 12a only. Now, going back to the quadratic formula, what we have here is I took a quadratic, I found its factors, and if you take those factors and I FOIL those together, I'm hoping that you guys would see that I got 2x squared minus 8x plus 2x minus 12. Does that seem about right? Yes or no? No, that's not right. That should be a minus 3. It's a minus 3x. I was wrong. That looks a little different than the last time I ran through. I didn't draw my lines to show my work. That would explain some things. Those are those two. Then it becomes minus 3x and then actually plus 12. So I had changed this up from last hour. But if I add the two middles up, I get 2x squared minus 11x plus 12. So what I want us to do today is not factor it, because this is factorable, is I want you guys to see, or we're going to verify that factoring, quadratic formula, completing the square are all viable options. And if I go back to the beginning there, I'm going to change colors so that we can see it. If I go back all the way up to the factors here, and I set each of those factors equal to 0, I think everybody would recognize that x equals 3 halves and x equals 4. Can you guys agree with that? If I set each one of those top factors equal to 0. So what we're going to do then today, guys, is we're going to take the quadratic here, and we're going to apply the quadratic formula to it, and that's going to allow us to find the exact same x values. The zeros are the functions, the factors, and all of those things. So, I have a set of 4 steps. I think we wrote those down last time. We just never got around to actually implementing them. So, first thing, I need you to set the quadratic equal to 0. So sometimes that 12 might be on the other side. Or there might be another number where that 0 is. Bring everything to one side, set it equal to 0. I want you to list A, B, and C. And then I want to write down the formula. I cannot stress enough that when you're using a formula, whether it's quadratic formula, slope formula, point slope formula, slope intercept form of a line, all of those things, always write it down. The way I am listing these steps is a way for us to know what the pieces are and what the puzzle is. And if you know where those pieces go, and you know what the pieces are, then it's just easy to plug them into the right place and be done. You just got to use your order of operations at that point. So, if I ask you, now remember, this is all based off of a quadratic. Ax squared plus bx plus c. Right? General form, or standard form, sorry, of a quadratic. Part 1 is done. Part 2 says list A, B, and C. A equals, B equals, C equals. What is A? It is 2. B is negative 11, and C is 12. Be very careful. I do not ever want you to see or write that a is 2x squared. And b is a negative 11x. The x squared and the x are the variable parts. They are not the coefficients, which a, b, and c are. Be very careful. It seems like every year there's a group of kids that want to list the x's with it. No, it's just the number in front. Number 3, write down the formula. What is the formula? X equals opposite of b. Don't use negative. Plus or minus?
The square root.
Square root?
B squared minus 4ac.
B squared minus 4ac.
That's be all over 2a.
And it will be all over 2a. Notice we got a formula. We have the values that go into that formula. Now it's just simple evaluate for our numbers. So, the way I like to do this is I like to use parentheses every time I substitute. When you play coach, use parentheses. What is the opposite? What is b? It's a negative 11. So I put a negative 11 inside parentheses. It has a negative out front. That will change it. Plus or minus square root b squared. Nope, not b squared. What is b again? Negative 11 squared minus 4 times 2 times 12. Make sure that your square root or your radical goes over the whole entire group. And all of this is over 2 times 2. Guys, this is a viable option because a lot of us, they see a quadratic here, and they see a is not equal to 1. And we're like, I don't want to factor that. So we'll just use the quadratic formula. Perfectly fine. Let's start cleaning this up. What's the opposite of a negative?
Positive.
So it's 11 plus or minus square root. What's negative 11 squared? It's 121. Minus 96 because it's 8 times 12. 96 all over 4. What's 121 minus 96?
25.
Square root of 25 all over 4. That is x equals 11 plus or minus 5 over 4. And 5's a pretty nice number, yeah? So I got to split it up. 11 plus 5 over 4, which is 16 over 4, which is 4. Hey, that's one of our answers. 11 minus 5 over 4 equals 6 over 4, which is 3/2, and that is our other answer. Do you guys recognize that those are the answers that we started off with? Now, these were relatively nice numbers. Quadratic formula, remember, works with imaginary numbers, things that will have square roots, so irrational numbers, non-factorable quadratics. Now we're going to move on to lesson 12. This is part A. It's angles and diagonals. That's what we're going to talk about today. So, what we need to do here is we're going to look at polynomials, and they're going to be convex polygons. Polygons, guys, remember, come in two forms. Convex and concave. Concave is when someone knocks one of your vertices inward, so it points inside. Convex is when they're pointing all outward.
Do you have any lead?
So, convex means all of the vertices are pointed outward. So all of this is going to work for those. Okay? Also, we should highlight the fact that the number of angles equals the number of sides. So a triangle has 3 vertices and 3 sides. A quadrilateral has 4 sides, 4 angles. Pentagon has 5 sides, 5 vertices. Makes sense. Now, all convex polygons have what we call interior and exterior angles. This picture or diagram here highlights that. I stands for interior, E stands for exterior. So, what we have here, guys, is that I is inside, E is outside or exterior. Now, it's very important that you guys understand that exterior angles are formed by taking one of your sides and extending it outside of your object or your polygon. Now, if you guys are observant, yes, I can walk out straight here and turn back this way. That is E. That is an exterior angle. But what you might also observe is that if I walk this way, I then can turn back this way, and that is also E. If you notice, they would actually be vertical angles. The biggest thing you guys have to realize, though, is that you don't use both. It's very directionalized. You're only going one way. Now, what does this mean? So either I'm going to start with where I'm on the red and walk straight out that way and turn to the left, or I'm going to be on the purple line, walk it down, and then turn to the right. One's going left, another one's going right. Now let's stick with the red. So if I started my walk, let's back up. If I start my walk at this vertice right here, guys, and I walk, let's say this is my pool, okay? I have a very triangular pool. If I walk from here to this vertice and I want to walk around my pool, wouldn't I have to turn like this angle of E is facing? If I wanted to walk at the perimeter of my pool, I would have to walk or turn to the left, an exterior angle. Would you guys not agree that once I got all the way up to this vertice, I would have to make another turn?
Yeah.
And that turn would be based off of that angle. Would you guys agree? Exterior angles at each vertice are different, potentially. So they're not in the same place or the same location. They're not the same size. So now I'm walking, I get down to here, and I'm at the edge of my pool. I got back to where I started, but I want to be facing the same way, so I turn again. It's a little hard to demonstrate this on the slide here, but guys, what did I just do? If I started by facing this direction right here, I turned, walked, turn, walk, and turn again. Which way am I facing?
The same way you started.
The same way I started. That means I went how many total degrees? 360.
180.
I just went 360 degrees. I'm going to pause the video. I'm going to do the same thing walking around the desk, which is a quadrilateral. It doesn't matter if it's a triangle. It doesn't matter if it's a quadrilateral. It doesn't matter if it's a dodecagon. Oh,
It's a
12-sided?
Yeah.
So it's a 12-sided object. If I walk around my object and keep turning, I will eventually end up back where I started 360 degrees later. So what does this mean? It means this. It means, bullet point number 2 here, the sum of the measures of the exterior angles. I want you guys to underline that. Exterior angles of any convex convex polygon is 360 degrees. Very important. Another big idea or concept is this first line. The sum of an interior angle and its exterior angle has to be 180 degrees. Now, why is that true? I think everybody would agree that if I took this side and extended it out, I would have an interior angle and an exterior angles. They form a straight line, and all straight lines are
Perpendicular.
Congruent.
180 degrees.
it's 180 degrees because it's straight. Yes. So angle I plus angle E will equal 180 degrees. So those are two important formulas or things to know. Part of your questions is they're going to say, you have a 15-sided polygon. What is the sum of the exterior angles? Your answer is 360. Done. Should be one of the easiest questions that you guys would have to complete on a quiz or a final. Now, also on this slide, I'm asking you, how many degrees does a triangle have?
180.
It's 180 degrees. So there's 180 degrees. Why is this important? Well, let's come up with this idea that maybe I'm not asking for exterior angles. I want to know the interior angles. That is a what shape on the screen right now?
Rhombus. Pentagon.
It's a pentagon.
Circle.
I got a question. How many angles, if I took this angle plus this angle plus this one plus this one plus this one, how much does it add up to?
5.
There are 5 angles, but how many degrees are each one? Total, altogether.
360.
Here's the thing. The more angles I have, the higher the value of the interior angle is going to be. Exterior never changes. I'm basically doing 360 all the way around. What if I told you that it's just a simple task of creating triangles? What I would need to do is I can take one of your vertices and connect it to another vertice. That same vertice gets connected to all other vertices that it's not already connected to. Those are diagonals, guys. But do you guys notice that these two are already connected? And so are these two down here. So the only thing left for this particular vertice is to connect the two that are opposite or farthest away. How many triangles do you see?
3.
Guess what?
4.
3 times 180 will equal
540.
540 degrees. How many degrees are inside a pentagon? 540. Mr. Konchak, how does this work? Okay. Watch and learn. Would you guys agree that this particular triangle has 180 degrees? Because all triangles have 180 degrees. This angle, listen, this angle and this angle add up to 180. Moving to the center triangle, these 3 angles add up to 180, and again, those last 3. Here's a really cool thing. The angle that is built right here has been split into 2 parts. But guess what? This particular angle has been accounted for in the left triangle. This side of the angle is taken into account in the middle triangle. So this whole entire angle has been taken into account for. The same thing happens here. Whoops. Here. And even this larger angle is just the sum of the three angles at the bottom, which are already taken care of in the triangles themselves. I could care less how big they are, how small. I know that overall they're added together. They add up to 180 individually. So therefore, they're all taken care of. The sum is all there. So, if I had a quadrilateral, 4 sides, how many diagonals, or how many triangles can I make? Split it right down the middle. I got 2 triangles. 2 times 180 is 360 degrees. Think of a triangle, or a rectangle, sorry. 90, 90, 90, 90 is how much? 360.
Wait.
Got a question. If I wanted to build a formula, how can I build that formula? So let's come up with some formula here. There's got to be an easier way. We already did this one, pentagon. I was able to make how many triangles? 3. So there are 5 vertices in this one, 3 triangles. 3 times 180, right? This is a what? Hexagon? There are 6, put it off to the side, 6 sides. 1, 2, 3. I connected it 3 times. How many triangles? So it's 4 times 180. That's 720, huh? Ooh, look at this guy. How many are there?
7. Yeah, 7.
There's more than 7 sides.
8. Oh, 8 sides. 7 triangles. 9 sides.
9 sides? Okay, so 9 sides. 1, 2, 3, 4, 5, 6, 7.
8 triangles.
So there are 8. 1, 2, 3, 4, 5, 6, 7, 8.
8.
Something's not right. How many sides have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 sides.
Oh, you're missing 2.
Okay, wait. Someone just said something.
14,
What's the pattern? How many times do I multiply by 180?
8. Oh, it's 2 less than how many sides?
2 less than the number of vertices or sides. So, what is the formula? Number of interior angles equals. I think there's 180 in there somewhere, right? What's the formula though? N for the number of sides
N minus 2.
minus 2. There's your formula. So if I told you we're looking for 15-sided object, how many interior angles? 15 minus 2 is 13 times 180. You got it. How many exterior angles in a 15-sided object? Or convex polygon?
Yeah. 15.
Exterior angle. Convex polygon. Always. Stuff before this, guys. Interior, use the formula. Exterior, always 360 degrees. So, the last one, guys, is we're going to talk about diagonals. Guys, the diagonals are those lines that we just drew. But here's the thing. It has more than just 2 diagonals. Guys, definition of a diagonal means connecting any 2 non-adjacent vertices. These 2 are adjacent vertices. They're part of the outside of the shape. These 2 that are across from each other are non-adjacent. That creates a diagonal. So, I have 2, 3, 4, and 5. So if there are 5 vertices, there are 5 diagonals. Hexagon, 6 sides. How many diagonals? 1, 2, 3. 4, 5, 6, 7, 8, 9, 10? I get 10. Should be 3 from every single one. Yes. It's 10. Now we have to go to a 10-sided object. This is where things get a little crazy. 1, 2, 3, 4, 5, 6, 7. Each vertice will have 7 lines coming from it. But guess what? One of those connections is already taken up now. So it keeps falling, doesn't it? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I got 26, but I don't know if that's right. That's a problem, isn't it? Look at that. It is all over the place. And you mess up, you got to restart because I lost track. There's got to be an easier way. Now, we could sit here and I could draw everything from a four-sided all the way up to 10 and say, hey, guys, come up with a formula. But I'll just give it to you guys. Number of diagonals equals n times n minus 3 all over 2. Now, does it work? 5 sides. What's 5 minus 3?
2.
So 5 times 2?
10.
Divide by 2. 5. It worked. What about 6? 6 minus 3? And 3 times 6?
30.
Uh-oh.
3 times 6 is 18.
3 times 6 is 18.
Divided by 2.
Times 6. So it should be only 9.
Yeah, 'cause
We messed up on that one. Or I did.
those 2 have 4.
Did I draw the same line twice?
Yeah. Yes, you did.
I think I may have.
It's right here. It's right here.
I should not draw. This only has 9. But there's your formula, okay? Your homework, page 95, 4 through 8, 10, and 11. Have a great day.